All right, let's dive into a process that pretty much shapes our entire modern world. From the sharp tools in a surgeon's hand to the crankshaft in your car's engine. It is incredibly powerful, amazingly precise, and it's happening all around us, usually just out of sight. So let's pull back the curtain on the hidden world of industrial grinding.
I mean, just look at that. It's pure, raw power and intense energy all in one shot. At its very core, grinding is just about removing material with abrasion. But as you see those sparks fly, what you're literally watching is thousands of microscopic cutting points shaping metal with unbelievable precision.
And the speeds we're talking about are just staggering. Get this. The surface of a totally standard 8-inch bench grinder wheel, it's traveling at over 65 miles per hour. Yeah, that's highway speed. So this isn't just like sanding a piece of wood, it's a high-stakes, high-velocity machining process. And that really sets the stage for everything we're about to get into.
Okay, so to really understand how this all works, we have to deconstruct the tool right at the heart of the process. Let's take a look at the anatomy of a grinding wheel, because trust me, it's a seriously sophisticated piece of engineering, way more than just a simple spinning rock.
The real work, the magic, is all done by these, the abrasive grains. A grinding wheel is basically this solid, porous tool made up of millions and millions of these tiny, super sharp particles. Every single one acts like its own microscopic cutting tool, slicing away impossibly small chips of metal. Now, you can't just use any old grain. The type of abrasive you use matters a lot. For most steels, the go-to workhorse is aluminum oxide. It's tough, it's durable. But if you're working with harder stuff, say cast iron or non-ferrous metals, you need to bring out the big guns, the even harder, more brittle silicon carbide.
Next up, you've got grit size. And honestly, the easiest way to think about this is exactly like sandpaper. A low number, something like a 24 grit, means you've got coarse grains, therefore removing a lot of material really fast. A high number, like 120, means you've got these tiny, fine grains for getting that beautiful, smooth surface finish.
And here is a super crucial point that, trips a lot of people up. The grade of a wheel, it doesn't actually refer to how hard the abrasive grains are. Nope, it's all about the strength of the bond that's holding them all together. A so-called soft wheel actually releases its dull grains easily, exposing new sharp ones, which makes it act more aggressively. Kind of counterintuitive, right? Then there's the structure, which is just the spacing of the grains. Imagine the difference between a really dense pound cake and a light, airy sponge cake. Well, an open structure wheel is like that sponge cake. It has more empty space, more porosity, and that gives all those little metal chips a place to go so they can be washed away, which keeps the wheel from getting all clogged up.
And finally, holding this whole thing together is the bond, which is, it's basically the glue. The most common types are vitrified. That's a hard, rigid ceramic bond that's fantastic for precision work. And then there's resinoid, which is an organic bond that's a bit tougher and better for the really high-speed, heavy-duty stuff.
So when you combine all of those variables, the abrasive type, the grit, the grade, the structure, and the bond, you start to realize that running a grinder isn't just some simple mechanical task. No way. It's a really complex balancing act. It's a true art form, but one that's guided by some pretty deep scientific principles.
Which, of course, brings us to the million-dollar question, the one every single machinist has to answer for every single job. What are the right speeds and feeds to get that absolutely perfect result?
And the answer is, well, it's complicated. As you can see right here, there are no simple cheat sheets for grinding. The range of recommended speeds, which we measure in surface feet per minute, is massive. Cutoff wheels might be screaming along at 16,000 SFPM, while a delicate surface grinding job might be down around 4,000. There's just no one-size-fits-all answer.
It's just like the Abrasive Engineering Society says, the best result depends entirely on the application. The machinist has to think about the material's hardness, the finish they need, how rigid the part is, the coolant they're using, and even how long they want the wheel to last. It's a dynamic, complex calculation every single time.
So what happens when that super careful balance gets, thrown off? Let's look at some of the most common grinding problems and see how a really deep understanding of the whole process helps us solve them. A classic problem, burning. That brownish or bluish discoloration you see on the workpiece, that is not just cosmetic. It is a big red flag for thermal damage. It can actually change the metal's hardness and its internal stresses, which could potentially ruin the entire part. And the causes? Well, they trace right back to the anatomy of the wheel we just talked about. Your wheel might be glazed or loaded, which just means the abrasive points are either dull or they're clogged up with metal. so now it's causing more friction than actual cutting. Or the operator might be pushing too fast. Or maybe the wheel's grade is just too hard for that particular job.
So the solutions are pretty logical, right? First thing you can do is dress the wheel. That's a process that basically breaks away that dull, clogged layer to expose fresh, sharp abrasive grains underneath. You can also, of course, slow down the feed rate, or just reduce the overall speed to lower the heat being generated.
Okay, another frequent headache is a poor surface finish. You're aiming for that perfect, mirror-like surface, but instead it comes out all rough or scratched, or it's got some weird pattern on it.
And again, the culprit is almost always a mismatch in one of those process variables. The grit size might just be too coarse for the fine finish you want. The speed could be too high. Or maybe your coolant just isn't getting in there and flushing away those tiny metal chips, which then get dragged across and scratch the surface.
And the fixes? They're just as direct. Switch to a wheel with a finer grit. That's an easy one. Slow down the relative speed between the wheel and the workpiece. And of course, make absolutely sure your coolant is aimed correctly and flowing with enough oomph to keep that cutting zone clean.
We've talked about the art and the science, but all of this power, all of this speed, it demands absolute respect. So the most important part of grinding is, without a doubt, doing it safely. And that really comes down to a few very, very specific numbers.
On any bench or pedestal grinder, you've got key safety components that are mandated by OSHA. Two of the most critical are the work rest, that's what supports the piece you're grinding, and the upper tongue guard. Now, their precise adjustment isn't a suggestion, it is an absolute requirement.
And this is the part you absolutely have to remember. The work rest must be adjusted to have a maximum gap of 1/8 of an inch from the wheel. Any wider than that, and your workpiece could get sucked in and jammed, which could shatter the wheel. The tongue guard needs to be within 1/4 inch, and that helps contain those fragments if the worst actually happens. These are not just numbers. They are, quite literally, lifesavers.
So, the next time you see a perfectly smooth, precision-engineered metal surface, just take a second to appreciate the invisible process that probably created it. From the scalpel in a surgeon's hand to the crankshaft in an engine, how many objects in our everyday lives really depend on this hidden world of high-speed precision? Makes you think, doesn't it?